Hello, everybody. Welcome to episode 3 of the SpaceML Speaker Series. Today, we welcome Gonzalo Mateo-García, who is going to be presenting his work on ML4Floods. Gonzalo has been with the University of Valencia working on this, but is also working with Trillium on the ML4Floods projects and various other projects. So welcome, Gonzalo. Thank you for making the time, and take it away.
Okay. So yeah, thank you for having me for this SpaceML Speaker Series. So so Ansel has already presented me. So I'm going to talk about the work that we've been doing over the last year on that is called ML4Floods, which is an end-to-end toolkit to do flood extent segmentation that is especially designed for emergency response. So this is the outline of the presentation. First, I'm gonna give some motivation of the of the work that we've been doing and a summary so that you get an idea of what you could use ML4Floods to. Then I will talk about the background that led us to develop ML4Floods. Later, I'm gonna outline the different components of the ML4Floods toolkit, and I will show you some Google Colab tutorials that we have available as a live demo. And finally, I will show our latest results, trying to map the floods that happened early this year in Australia. So this is an image of one of those floods that happened in the city of Lismore. Actually, there has been 2 peak events over in these Australian floods, especially in this city. So actually, this city was flooded first around the 26th of February, and later in the 29th of March. So you can imagine that when one of these terrible situations happens, one of the things that are needed to coordinate the response are maps, right? So maps such as this one, that is produced with ML4Floods. So in this map, what we could see is which area within the city of Lismore is affected by floods, right? So we see which parts within that city are flooded. This is this image is produced is from the 31st of March and is produced using as an input satellite images. So in a nutshell, so ML4Floods is a toolkit for the first response community to produce actionable maps using machine learning. So the models that we use to do the segmentation are based on machine learning, on deep learning. So as I said, the input to the models are certain satellite images. So in this case, in the case that I showed you before, that I'm showing you here again, the image that we use to segment the flood is a Sentinel-2 image. So ML4Floods started is based on the work that we did in Frontier Development Lab in the FDL Europe 2019 research sprint. So in that sprint, what we wanted to do actually is to demonstrate that these maps can be produced directly on both satellites, right? So actually a satellite that is observing the Earth, if it has sufficient compute capability, it may be able to run this model and to produce the flood map online, so that it sends a response to Earth and minimize the time to response, right? So when we were prototyping this system, one of the main limitations that we have back on the day was that there wasn't a representative global data set of floods, right? That actually has pairs of images and flood maps. So that was one of the biggest contributions of this of the FDL 2019 research sprint, was the data set that we created. That is the one that I'm showing you on the screen now. And this data set is called World Floods, and it has Sentinel-2 images and flood maps from different locations around the globe. So that, and using this data set, we can show that the models that we trained to do flood segmentations are able to generalize to new locations, which is a main requirement if we wanted to do this on board. So this, the results of this work was published in Nature Scientific Reports last year. And so actually, what's the difference between what we did in FDL Europe and ML4Floods. Well, ML4Floods, it's a continuation of this work. Basically, it's so that what we've been doing over the last couple of years is to increase, to make the models that we have and the code base that we have more production ready, right? So in ML4Floods, what we have is there are a set of components to do actually end-to-end flood extent segmentation, right? So actually it goes from downloading the images to train the models and to produce vectorized outputs that could be used for flood response. And also the other big components of ML4Floods is a big data lake that is stored in the Google Cloud Platform, which currently have around 10 terabytes of data, and which has the world flood data set and also new flood maps that we have added since then, right? And new and also different data modalities that we have available. So this is the ML4Floods pipeline. So the different components that we have, I will go over them in a minute, and then I will show you also in the Google in the documentation of the package, so where we have tutorials to access the different bytes, right? But first, I want to talk here about the different kinds of users that this toolkit is designed for. So one kind of users would be what we could be like flood scientists, or people that are more interested in improving and understanding the models, right? So in this, for flood scientists could use ML4Floods to actually import data from past flood events that they do have this data, right? They could also fine tune or retrain the models that we have on their specific areas of interest, so that the model perform better for their specific needs. And also it's possible to extend the pipeline to work with other data modalities. And the second kind of user is what we could say like a first responder, which what the main thing that is more interested about ML4Floods is that they could be used to produce fast and reliable flood maps that are able to cover large areas, right? So using these flood maps, they could just coordinate the response, they could do impact analysis, and they could also monitoring the floods over time, right? To see how the water is being receding or not. So I'm gonna go now through the different parts of the pipeline. So the first thing that we need is like data ingestors, right? That they take data from different sources and ingest it in our Google Cloud data lake. So data it's gathered for training from Copernicus Emergency Management Service, and the Copernicus Emergency Management Service, they published flood maps over areas of interest. And this data is actually the one that we use for then training, that we use as ground truth for training the models. And then the satellite data, it's now gathered from the Google Earth Engine. And from the Google Earth Engine, we download Sentinel-2 images mainly for training the models, although for running inference, we are also using Landsat 8 and Landsat 9 imagery, and the models that we train with Sentinel-2 work reasonably well in Landsat 2. So once this data is ingested, is downloaded, is structured, right? That it's like the model that we call data enhancement is doing. So basically, it's structuring the data within our storage, right? And in this this structuring consists of for each AOI we have the Sentinel-2 image, the metadata of the flood, ground truth. We also have permanent water layers that tells us which water is permanent, right? And also the flood images. So using these two first part of the pipeline, what we have done is extending the world flood dataset to contain, so now it has more than twice the amount of flood maps that it has when it was published. So now we have approximately flood maps from around 1,000 different AOIs. And this is what I'm showing you here in this map. Showing you in green the flood maps, the images and the flood maps that we're using for training. In red, the ones that we use for testing, and in black, the ones that we haven't been able to create yet. So this is how the data set look like. So for each of these locations, we have a Sentinel-2 image and a corresponding ground truth, which is which pixels have water and which doesn't have water. So this one is over a location in Greece, and this one is from a location in Finland. This one shows a flood over Madagascar, and this one is from a flood event in Uganda. So with this big data set, like the third component of ML4Floods are the different modules that are used to train and to run inference on new images, right? And so in this part of the pipeline, I will show you later how it looked like in the tutorial. But we could also compute metrics, right? So actually to measure how well the model does in comparison with the ground truth that we have available. And yeah, and we could also run different types of experiments, and also with monitoring, we could monitor the training. So one of the things that we've been doing with this new part of the pipeline, one new thing that we have done is to produce new models that are able to that do multi-output binary classification. And that means that we have a network that on a single pass, given a Sentinel-2 image, it produces a binary mask saying if the pixel is cloud contaminated or not. And another, so it produces two binary maps, one for the cloud probability and another for the water probability. And the good thing of tackling the problem as multi-output binary classification is that we could have pixels that are at the same time could be masked as a cloud, but also they are predicted at water. And the reason why we could train these models is because the ground truth that we are using for training these neural networks come in many cases from SAR images. So actually the ground truth is not affected by cloud contamination. And this is an example of a flood in Australia. What I'm showing you here in the left-hand side is the Sentinel-2 image, and in the right-hand side, the output of the model. And we could see here in the bottom left, in the bottom right corner of the image, that actually this image is affected by thin clouds, but we could still see the underlying water that the underlying flooded areas, right? And what we see is that the model is able to produce relatively good results on this location. Okay, so now it's time to go and see the documentation of the package and to do a live demo. So I'm gonna go. So the documentation of the package is found in this website in ML4Floods. Is also linked from the SpaceML site. And what you could see here is just you have first a large introduction explaining like the purpose of the toolkit. As you may imagine, you have instructions to install the ML4Floods package. As you may imagine, it's just doing a pip install since using Python. And here there are different tutorials. So these different links link to a different tutorial to do different things, right? So for example, there are tutorials for doing data preparation. So all the things that I've told about ingesting flood maps. So if we click here, we see that in this tutorial, we could download images, flood maps from the Copernicus Emergency Management Service and the corresponding Sentinel-2 images. We have tutorials to create the ground truth. We have tutorials to train models, actually. That, for example, this one, we could go here on the right-hand side are the contents, right? So actually, if I click training, we could see that after a bunch of steps, we could start training a model. We are using PyTorch Lightning for training the deep learning model based on the workflows dataset. And as you could see here, these are the steps of the model training. All of these tutorials can be open in Google Colab, so you could try them by yourselves. So in the MLOps part, there are things for running metrics, as I said before, and also to run inference on a new Sentinel-2 image. And the tutorial that I wanted to to show you with a little bit more of detail is this one, which aims to run inference on a time series of Sentinel-2 images. So if we open this tutorial in Google Colab, what we see is that so what we try to do in this tutorial is you set up a time range and also an area of interest that you wanted to forecast the floods, and it will download all the Sentinel-2 images over this AOI. The ones that are actually, it will download only the ones that doesn't have too many clouds. And once those images are downloaded, we could just load the model and run inference, right? So if you run this tutorial, what you will see, if you run it correctly, if not, you feel free to open an issue in GitHub or send me a message, right? So one of the first things that you will see is the time series of the cloud coverage over this AOI, right? So actually, each of these points says that for this day, there is a Sentinel-2 image that has a mean cloud coverage of around 15%, right? So actually, over this AOI between the 15th of January and the 1st of March, there are several Sentinel-2 cloud-free images, and there are other images that have a very high cloud that are very cloudy, right? So what we will do in the next steps is to download all these images, all these Sentinel-2 images. This is done here, right? And then here that it says downloading. And then the second part of the tutorial, what it does is actually loading the model from the pre-trained model that we have, and actually and then looping all over the different images, which is what it's doing now. Here, this loop that actually goes over all the images that we have download. And so if you do this correctly, and we have also some plots there, and what you could see is for this AOI, the different images and the corresponding prediction. But also, so it more or less that, but also this output is then vectorized, right? So actually, if we go here on the cell at the bottom, actually we could see the output in a interactive map, right? So actually, this is the flood map from the 28th of February, and we could take another one. I think the peak of the flood was around the 15th of February. So actually, we could see here which areas are affected by the flood. Okay. So now, before we conclude, I wanna just show you our latest results mapping the floods in the southeast coast of Australia. That, as I said you at the beginning of this talk, this happened. There were two very big flood peaks that happened at the end of February and at the end of March of 2022. So what we have done is something very similar to what is shown in that tutorial. We have produced a set of AOIs, of 54 AOIs, so more or less 900 square kilometers each one. And for each of these AOIs, we have downloaded the corresponding time series of Sentinel-2 images and Landsat 8 and 9 images. So between early February, so that we have some estimation of the amount of water that was before the flood, and from mid-April. And we produced around 1,300 flood maps for these locations. So in particular, I'm going to show you the results over the city of Lismore. This is also the mean cloud coverage over the AOI in Lismore. And again, we could see that we have, in this case, Landsat and Sentinel-2, Landsat 8 and 9 and Sentinel-2 images. And what we see is that after in these black lines, these are the two flood events, right? So we see that we have two images, one image that is only 2-3 days after the flood. And in this case, we have an image that is just 2 days, like 1 day just after the flood, that the cloud coverage is low. So how do these images look? This is how the Lismore AOI looked before the flood, so the 9th of February. And this is how it looked on the 2nd of March after the first flood event. We could see here that the city is very affected. And also, this is the Sentinel-2 image that we have after the second peak of the flood. So if we see this in more detail, what we see is that the vectorized output that we produce is relatively good. Maybe it's missing some flood traces here, but overall the predictions are good, and these are the maps that we are delivering. So this is basically all. What we have done also is we have this interactive visualization that you could also click and try. So if you go here, what you will see is that you are able to load the flood maps for the different locations and look how they look like. So that's all. I hope that you enjoyed the talk, and I want to thank SpaceML, which is a machine learning toolbox and developer community, which is building open science AI applications for space science and exploration. You could find the ML4Floods project and many other projects in spaceml.org. And I would also like to thank the different sponsors that made this project happen. So in particular, the FDL 2019 research sprint, which was funded by the ESA Philab. And we have also collaborated with other partners at UNOSAT and University of Valencia. So thank you very much. I'm happy to take questions.
Okay, if you want, I can start with some questions. It's true that first of all, I would like to thank Gonzalo and also ISA and FFD because the funding, because it's really good to see this kind of applied research that combine real problems with supporting to researchers that are starting their career. So it's really good. And during the presentation, I have some questions that maybe are related with what have you learned during the whole project, and also the further directions of the research that you can follow. So, for example, obviously you have worked only with Sentinel-2 data, okay, using the 13 bands that you have available in Sentinel-2, and that suggests to me if you have also learned for using these deep learning models, okay, that they can be really powerful, but you want to not only to obtain the final mask of the floods, you also want to learn about the problem that you have, the physics, and how to take advantage in, for example, future satellites. My question to Gonzalo is if you have analyzed somehow the model that you have obtained in two directions. One of them can be related with how to transfer this approach, how to transfer this model to new instruments that maybe they are or not so low cost, because usually that you want is to learn, okay, I have Sentinel-2, I have a lot of information, really good and accurate data, but I want to transfer these kind of models and that I have learned about the problem to cheaper, I will say, satellites. But I have seen that in Australia, you also combine Sentinel-2 with Landsat data. Mm-hmm. Even it's true that the model has been trained with Sentinel-2. So what do you think about which features are the best ones or which can be applied to a different sensor?
Yeah, so I think one thing that we learned is like for mapping water, the infrared channels are very important. So that's something that for people that is very familiar with remote sensing, it's kind of obvious. For people that is come from a machine learning background, they something that they found when they start training these models, right? So for instance, to actually transferring these models to an instrument such as Landsat 8 works very well because spatial resolution of Landsat and Sentinel is very similar, and also because there are some some of the bands, they have more or less the same bands, and they have the infrared bands, which are the ones that are more important in our experience to map flood. We have also tried to transfer these models to other instruments that only have RGB that only have RGB cameras, but in our experience, what it happens is like the performance, the model doesn't work that well, right? So actually, there is a big drop in performance when there are not infrared bands, and then also in the particular case that we were testing, it happened that the camera also has a very different spatial resolution and also has much less calibration than Landsat on Sentinel. And so in this case, the model was very difficult to transfer, and we need to label some of the images from that instrument to actually improve its performance.
Yeah, and also I assume that because you are solving two problems at the same time, because it's not only to have the best bands, spectral bands for detecting water, that is true that then the SWIR is really important, but it's true that you have also to detect the clouds that you can have in the images, no? Because you don't rely on in an additional or independent cloud mask.
Yeah.
You are detecting also the clouds that you have in the image.
Yeah. Yes. So we run it in a single pass to actually be able to produce at the same time the cloud probabilities and the water probabilities. And this is because in our experience, we see that Sentinel water tend to overmask, and in general, this is what you want for most of the problems that you're working with. But for this particular problem of detecting floods, where the image after the event is very important, and also is not as we see in the previous image, in one of the images that I show, in this one in particular, is that there are areas which actually are affected by clouds, but where we can see water, right? So in this case, if we use the cloud mask that is provided with the Sentinel-2 image, we will be missing these areas, and we will be able to produce flood maps that are not that we should be masking these places, right? So actually, by having a model that produces the two things at the same time, we could just compensate the different trade-offs and also produce more better flood maps that cover larger areas.
Also, I don't know, I have more questions, but I don't know if someone else want to ask something, or I will.
Yeah, maybe I do have some question. Thanks, Gonzalo, for the nice talk. About uncertainty, I mean, you mentioned the two typology of user that you have here. You have the flood scientist and the first responder. Mm-hmm. I guess that they expect that you provide some kind of uncertainty matrix somehow, or trust less in your results. So do you envisage to work on explainable AI? I mean, what would be the next step for you to I mean, to ensure that what we're producing are right and accurate enough for the user to adopt it?
Yeah. So we don't know exactly how we're going to tackle this. So we have some ideas. First is like, actually, when we are giving this to the Australian National Resilience Agency, what we are giving to them, so we are telling them, we're being honest, that we see that we are saying to them that this is an AI generated product, right? So it could be, there could be errors, right? So one thing that we are aiming to do actually is like in one of these in this kind of visualization, what we could do at the same time is show the Sentinel-2 image and allow the users to correct the areas which are not affected by clouds, right? Which are not affected by, so they could be able to edit these polygons and to correct the errors that they see manually checking. But yeah, at the end, there is a trade-off, because if you want to map large areas such as these ones, which is, I think there were like more than 100,000 square kilometers. You can't do this manually. I mean, in this case, you could maybe just fast checking that the model is working, But at the end, you need to if you want to do it this in that scale, you can't afford to look at each of these images. Yeah, and then about producing uncertainty metrics, what we see, so the output of the model is the water probability, and what we've been seeing is that the higher the probability, the more certain the model is, right? And in the paper that we are preparing now, we have precision recall curves, right? Where actually you could see the trade-offs between the amount of false positives and false negatives that you want, right? So actually you can change the threshold and then have a more conservative or less conservative product.
Okay, so you could play on the pseudo likelihood and thresholding this pseudo likelihood and,
yes,
and work towards like uncertainty metrics from this pseudo likelihood.
Yeah.
Okay.
Yes, that's one possibility, but we are very open to suggestions.
And from a pure deep learning perspective, I mean, do you have in mind any research activity so that you can directly infer via the network some kind of uncertainty matrix? Would that be feasible? I mean, what is the current trend in the literature on that? Do you have any insight or comment linked to that? Sorry, that's maybe a tough question, but
I mean, so for example, we've actually in the tutorial we have one example using Bayesian dropout to have some, because what happens is that normally out of the deep learning models, the probability values that you get are not very well calibrated. So that means that that probabilities are sorted, but the values that you get are not. So actually, it could be like, it's not that if the model is 60%, it doesn't imply that 60% of the time the model is predicting well. So actually, that's so when you go, for example, with Bayesian dropout, you could have. I think we have this. Let me see if you could have better metrics, right? I think this is an example that we have with probabilistic neural networks. I think that here at the bottom, problem here is that's very small, but so actually what we have here is not only the prediction, but also we could estimate the entropy of the different predictions. At the end, in this particular example, what we are doing is running 10 different it's almost like running 10 different models, right? And from the output of these 10 different models, you could compute entropies so that it tells you which areas the model is less certain. So in this case, for example, it's less certain of the areas within the boundaries of the flood. And that's more or less what is measured with the entropy. I think in this one, it was more or less a better example, because in this one it's showing, this one is very good because actually what we can see here is that in this snowy area, the model is very uncertain. And that makes a lot of sense because we don't have many images that have snow, because normally floods and snow doesn't happen at the same time, or maybe it does, but not very often in my experience. So what we see here is that, in this case, we are able to capture this, right? But still, as we see, we are not capturing other parts of the snowy area at the bottom. We're capturing one at the top, but this one, the models are all agreeing, right? So we haven't find a way to validate this properly, but I think that would be one way to go if we need to provide if we want to provide an uncertainty product.
Okay, thanks for the explanation. Okay,
awesome.
Over to you guys.
We're almost out of time, so I wanted to thank you for such an amazing session, Gonzalo. This has been great. It was super informative, and thank you for the great questions that have come through. I'm going to press stop on record, and we can continue chatting and say bye-bye quickly.